This is the second part of the first lecture of week 13, where I'll remind you what multiplication of two matrices means. So, first of all, let A be the matrix of the size, let's say, m times n, and B be the matrix of the size n times, let's say, r. For such case, when we have the number of columns of the first matrix is the same as the number of rows of the second matrix, we can introduce matrix multiplication A times B. So if A was Aij and B was Bij, then the product is a new matrix which consists of sums. Okay, Ij, so let's say L is from 1 to n, A, I, L, B, L, J. So this is a new matrix, and let's see what the size of this matrix. I runs through the number of rows of matrix A, so I from 1 to m, and J goes through the number of columns of matrix B. So this is a matrix of m times r, of the size m times r. So let's now look at some examples. For example, we want to multiply matrix 1, 0, minus 1, 3, 2, 1. And here the number of columns is 3, so we can multiply this matrix only by the matrix which has 3 rows, right? So let's say this is 1, minus 1, 0, 3, minus 4, 5. And it doesn't matter how many columns it has, so let's say it has 3 columns, for example. 0, 2, 3. So how multiply this? We construct a new matrix, and the new matrix will be of the size 2 times 3, right? Because here m is 2 rows, and r is 3 columns of matrix B. So when we multiply, we take the first row here and the first column here, and we multiply first element of this row by the first element of this row, and add second element of this row times second element, add third element times third element. So let me just write it just once. Plus 0 times minus 1 plus minus 1 times 0. And now to get, this is the first term of this matrix. Now to get the second term, we multiply the same way the first row by the second column. So this is 1 times 3, 0 times minus 4, minus 1 times 5, and add everything. So 3 plus 0 minus 5 will be minus 2. Again, to get the third element of this matrix, we multiply the first row by the third column. So 1 times 0 is 0, plus 0 times 2 is 0, minus 1 times 3 is minus 3, so overall it's minus 3. Now, how we get the first row of the resulting matrix. Let's see how we can get the second row. To get the second row, we take the second row of the first matrix and multiply again by all columns of the second matrix. So the first element will be 3 times 1 plus 2 times minus 1 plus 1 times 0. So this is 3 minus 2 plus 0, so this is just 1. Then to get the second element, we multiply the second row times the second column. 3 times 3 is 9 plus 2 times minus 4 minus 8 and plus 5. So overall it's 9 minus 8 plus 5 is 6. So 6 is the second term of this matrix. And to get the third element of the second row, we multiply this times this. 3 times 0 is 0, 2 times 2 is 4, 1 times 3 is 3, and add everything, we get 7. So the resulting matrix is, we need to calculate this one, just 1, minus 2, minus 3, 1, 6, 7. So this is the product of these two matrices here. For example, let's multiply this matrix by this vector we have the matrix with 3 columns and the vector has 3 rows, so the multiplication is well defined. And what is the dimension of the resulting matrix? This will be the matrix of just 1 column and 2 rows, right? So what do we get? To get the first term of this resulting matrix, we multiply the first row by this column. So 1 times 1 plus 2 times 0 plus 3 times 2. So overall it will be 7. And to get the second term, we multiply this second row by this column. So 4 plus 0 plus 6 times 2 is 12. So this will be 16. So this is again column vector, but of dimension 2. So, and this multiplication looks kind of strange, but it satisfies quite a lot of interesting properties which we have for numbers. For example, so let's write the properties of this operation of multiplication. So the first thing that, for example, we have associativity. So A times B times C, this is the same as A times B times C. And of course here, what I mean by the product, I mean that the product is defined, right? So here, the size of A, B, C is so that the products are defined. And also we have distributivity. So if we take matrix A and multiply by sum B plus C, then this is the same as AB plus AC. And also distributivity from the other side. So if we multiply this thing, we get BA plus CA. What else? So if we multiply, for example, some number by matrix A and then the resulting matrix multiplied by B, this is the same as to multiply the first A and B and then by this number, or this is the same as to multiply B by this number and then multiply by A. So we have these nice properties. And notice that here, for example, when we look at these two properties of distributivity, the order does matter. So in fact, in general, AB is not BA. In general, this product is non-commutative. For example, just take maybe simple things like 1011 times 0111. So we get the matrix, which is 1001 is 0, 1 here, 1 here, and 2 here. And if we now reverse the order, multiply first this times this, we get 0, 1 times 1, 1 is 1, also 1, 2, and 1 here. So you see the matrices are not the same. So this is very important, that the matrix multiplication is not commutative. So when you write, for example, distributive property here, be careful. You multiply B times A and you write B times A, no A times B. These are different things.